posted over the chat box, which will be addressed in the QA session. I welcome Mrs. Vidya V. Shankar, Head of the Department of Physics, to welcome the gathering.
Good morning, everyone. I am here to welcome all of you into this international webinar organized by Department of Physics, SVR NSS College, Vazhoor. First of all, I welcome our Honorable Principal, Dr. M.R. Renuka Madam, who gave us all the support and inspiration to start this webinar. Welcome, Madam. Now I have to welcome our chief guest and the resource person today, Dr. Navaneeth Poonthottathil, who had his PhD work on experimental particle physics, and now he is doing his postdoctoral work on Iowa State University, US. Welcome, sir, and thank you for accepting our invitation. Now I have to welcome all the faculties and students, research scholars who had shown interest in our webinar and joined us for attending the session. Welcome. Thank you.
Warm greetings from staff and students of SVR NSS College, Vazhoor, to all the participants. Respected resource person Dr. Navaneeth Poonthottathil, Head of the Department Srimati Vidya Shankar, Convener of the webinar Srimati Ramya S. Nair, my colleagues, dear students, and distinguished participants from various other institutions. I feel very happy to be here as the president of this international webinar on particle physics, organized by the Department of Physics of our college. I will not take much of your precious time, as I am not able to speak anything about particle physics. But I take this opportunity to appreciate the possibilities that webinar is giving to our students and other academicians to hear from an expert from great institutions and universities, both national and international. Our respected speaker, Dr. Navaneeth, is very generous to be with us today to elaborate on experimental particle physics. And also, I hope Sir will share some of his experiences in such an internationally reputed lab, which will definitely motivate our students. I would also like to congratulate my young colleagues of Physics Department, Srimati Vidya and Srimati Ramya, for organizing this international webinar, which will definitely beneficial to all the participants. We honestly appreciate all the participants for their enthusiastic participation. Best wishes to all. Thank you.
I request Dr. Navaneeth to join us.
Hi, thank you for the invitation. So, can you all hear me well? Okay, so I'll share my screen now. Hope you all can see my slides. So today I'm going to talk about particle physics. So I'll try to keep this talk as basic as possible and as short as possible. So going into the particle physics, before I go into the details of this subject, I would like to give you a idea about the length scale which I am talking today. So you all know about galaxies. You all might have heard about that. So in physics, we often study with galaxies and other large objects, right? So when you talk about galaxies, so we often use the unit of length scale in order to express the distance. That means the distance that we are dealing in such in such area of physics is very large. So you know that one light year is a distance traveled by light in a year. So that you can imagine that that distance is huge. So in for astrophysics purposes, we use that large length scales. But I'm not talking about that huge length scale today. So from coming from galaxies to the Earth, so you know that the elephant is the largest animal in the land, and you can sort of, I just put this picture to give you an idea about the length scale which I'm talking today. So you know that from an elephant to, when you're coming from to a squirrel, you can kind of think about that length scale in your mind, and then from there, if you're coming to an ant and dewdrop, so you can sort of imagine the variation of the length scale in this picture itself. So I'm not going to talk about the physics of a tiny object as small as a dewdrop. So I'm talking a length scale which is even smaller than a dewdrop. So for example, as I said before, I just want to give you an idea of the length scale. So you have to have an idea about the length scale which I'm talking today. So I just put these pictures. I thought it will give you an idea. So in a dewdrop, it's roughly, if you think about it, it's a 1 millimeter radius. So from, you know that dewdrop is basically water, and water molecule is made up of 2 hydrogen atoms and 1 oxygen. And if you take a water molecule, if you compare water diameter of the water molecule, it's a linear molecule. So if you measure the length of this water molecule, it is around 3 into 10 raised to minus 7 millimeter. So when you're going from a dewdrop to the water molecule itself, you can see that the length scale has reduced small, and we are dealing with such a small object. So we are not even talking about that. So from there, if you go to the hydrogen atoms, so size of hydrogen atoms is around 10 raised to minus 7 meter. And from there, if you go, the hydrogen atom is consisting of 1 electron and 1 proton. And if you go to the nucleus of hydrogen atoms, you can see proton, and the proton is basically in the if you compare the size, it is in the order of 10 raised to minus 13 millimeter. And this proton is made up of quarks, and you know that it is 2 u quark and 1 d quark. I will talk about these quarks later on. And the length scale of that is around 10 raised to minus 15 millimeter. So today in this talk, I'm going to talk about the particle physics, which basically comes in the range of this length scale. So you know that it is very extremely small length scale, and the physics of these particles are very fascinating at that very small length scale. So in the right hand side also, I put small pictures to give you an idea. I'm not going to talk about that details. In case if you want the slide, I can give you after this talk. So you know that we all know about this periodic table, so which is basically the fundamental building block of chemistry, right? So you all might have studied a lot of chemistries using this, you all study different bonding between these different elements in the periodic table. So so chemistry, so all the fundamental chemistry is basically based upon this table. So here on the right hand side, I again want to give you a the length scale in a different unit. So suppose that in some unit, if you consider the size of an atom is 1, in some unit, you forget about the unit, you just take it as 1. So then the nucleons means proton and neutron together, the size of the nucleons will be 1 by 10,000 of an atom. So, and then from the nucleus, if you just take a proton, that will be like 1 by 100,000. And if you just uh, go sorry, and if you just go through the go to these like quarks and electrons, and the size is further reduced, and which is actually around 1 by 10 lakhs. So I'm can you all see my slide? Can someone message?
Yes, sir.
Someone is saying no and someone is saying yes. I don't know.
I think it's perfect, Navaneeth. You may please proceed.
Okay, thanks. Okay, so so I just want to tell you, so the length scale which I'm talking today will be on that order. So okay, so I'm coming into the elementary particles. So as I explained, all the building block of this chemistry is based upon the periodic table. Like that, in particle physics also we have a periodic table. So it's not a periodic table, but I'm just saying it like that as a comparison to the chemistry periodic table. So here you can see the particle physics, all the fundamental particles can be broadly classified into two categories, fermions and bosons. So if you look at the if you look at that red column and the blue column, those are bosons, and except everything is fermions. So fermions and bosons are the two classifications of the particles, which based upon some statistics. You might study it in a detail of the statistics in the statistical mechanics later. If you don't, I'm not going into that detail. So and the fermions are quarks and leptons are basically fermions. Fermions are generally the particle which have half integer spins. So you have three generations of leptons: first generation, second generation, and third generation. And the first generation quarks is basically up quark and d quark, and then you have second generation quark, which is charm quark and strained quark, and the third generation you have top quark and bottom quark, or beauty quark. You have different, the beauty and bottoms are same. And then corresponding to that, you have 6 leptons also, which are electron and muon and tau, and corresponding to that electron you will have an electron neutrino, and muon, corresponding to muon you have a muon neutrino, and corresponding to tau you have a tau neutrino. And along with that, these 6 plus 6, 12 particles, and there are gauge bosons, and the bosons are responsible for the forces between these particles. So I'll talk about these the functionality of these different bosons in the coming slides. And then you might have all heard about the Higgs boson, and Higgs boson is the particle which give masses to these elementary particles, so which is discovered in CERN in 2012. And so this is the this we called together, we call the standard model of particle physics. Standard model of particle physics basically deals with the particles and the interaction between particles, and which will also tell you how the particles get mass, and how it involves in different interactions. So the standard model of particle physics aims to explain the universe at its most fundamental level. So this is the very fundamental thing. So everything in the universe is made up of this, these particles. So this is the this is a standard model of the particle physics. Is the is a physics that explains the universe at its very fundamental level. So I mentioned about the length scale that we are going to talk today about, in the order of 10 raised to minus 15 meter. So when I talk about the length scale, I would like to give the time scale of the process of the physics process at this very elementary level. So the typical interaction could be as short as 10 raised to minus 23 second. Typical strong interactions, I will talk about that later. So, or in total, you are dealing with a very complex. You are trying to understand a physics of some particles, which is whose length, its length scale is extremely small, and the lifetime is extremely small. So this is very complicated thing. So you know that every particle, associated with every particle, which will have a wavelength, that's called the de Broglie wavelength. So which is proportional to, which is defined by h by p. It's a very fundamental thing, where p is the momentum. So you all know that in order to see an object, so what we need is a source whose wavelength is comparable to that the size of that object. Then only we can see that object. So in modern microscope, like an electron microscope and TEM, so you can see the molecular level, but if you cannot see the fundamental particles. As of now, I have I've read that you can see an individual atom, but you cannot see further down into an atom. So because you need a higher some source which has high resolution. So how do you probe these fundamental particles? As I mentioned, these particles are extremely small. How do you probe them? So in order to probe them, so you need particles which are having higher momentum as a source. So suppose, how do you create a particle with higher momentum? You need to make accelerators. So when you make the momentum high, you will get a smaller wavelength, so that you can compare. You can see all the all these particles. You can study the physics of all these particles. So that is the requirement of accelerators in particle physics. So like I mentioned in energy scale and the length scale, I would like to mention something about energy scale. What are the energy of these particles? So you know that using Einstein's equations, so energy can be converted into mass, and mass can be converted into energy. So for example, if you just plug in the fundamental constants of the electron mass and the velocity of light, so you can calculate the energy, which is actually 81 into 10 raised to 15 joule. But in often particle physics, we don't use this unit. Instead of that, we use electron volt. The 1 electron volt is the energy acquired by an electron when it is accelerated to 1 potential, 1 volt potential. So you can convert this joule into milli electron volt just by multiplying the Coulombic charge. So you will get 0.5 mega electron volt. That's the mass of this is a unit of energy, but as I mentioned, energy and mass can be related. So in particle physics, we often use the unit of energy to express the unit of the mass of this particle. So the electron, we say that it's 0.5 MeV. The mass of electron is 0.5 MeV. MeV means mega electron volt, and for proton, it is actually around 914 MeV. So these are extremely high energy as compared to as compared for a small particles. But if you consider, and if you convert 1 kilogram and the calorie of a 1 kilogram sugar into this unit, it will be around 10 raised to 13 mega electron volt. So which is actually 10 raised to minus 7 tera electron volt. So you can understand from this that these energies are extremely high when we are talking about these tiny particles. So okay, so now I will move on to different forces in nature. In order to understand the complete picture of the standard model, you need to understand the interaction between these particles. So how these particles interact together? There are 4 forces in nature, which are gravitational force, strong nuclear force, weak nuclear force, and electromagnetic force. So I mentioned in the previous slide that the physics that explain the interactions of these particles comes under the standard model, but the gravitational force, which will not come under the standard model, which is a separate thing. So people are trying to bring the gravitational force also into the standard model. That is what we used to call the grand unification radiation and other kind of other complex things, which as of now we haven't solved that issue. So just put in mind that the gravitational force is not a part of standard model. So besides that, we have strong nuclear force, weak nuclear force, and electromagnetic force, and I will explain about these forces in next few slides. So gravitational force, we don't know about the gravitational. I mean, we don't know about the so okay, one more thing which I would like to tell before I go. So during every forces, some particle is exchanging between these particles. Those are called these bosons. So in my first slide, so you have seen this photon, W plus and W minus, Z0 and gluon. These are the particles which exchange between these particles during a force. So whereas during the electromagnetic force, the exchanging particle is called photons, and during weak nuclear force, those particles are called W bosons and Z boson, and for the strong nuclear force, it is called gluon. Okay, so in gravitation, during the gravitational force, we don't know the gravitons are existing, but there are experiments and there are studies are happening. So so just for the time, you just assume that if it is graviton and the gravitational force is responsible for we explain all the solar system, black hole, galaxies and everything using the gravitational force. And then going from the gravitational force to the strong nuclear force, so strong nuclear force is responsible for like the higher the force which is responsible for binding the nucleons together inside the nucleus. So you know that inside the nucleus there are protons, right? So protons are positively charged particles. So if and the nuclear size is 10 raised to minus 15 meter. You know that I actually explained that in my first slide. So why the proton? If the protons are positively charged particles, and if it is there inside the nucleus, why the protons are not coming out of this nucleus? Because it by Coulomb's law, you know that the positive charge particle or like charge particle will repel, right? But it is not coming outside. Protons are still positive charge, but it's still confined inside the nucleus, right? So I leave that question with you. You can think about that. Why it is so? Maybe you will understand it, if you listen to my next few slides. So then we will go to the electromagnetic force. What is the electromagnetic force? All the atoms, chemistry, light, magnet, everything is working the interaction happening in these things are electromagnetic interaction. So during an electromagnetic interaction, the exchanging particle is photons, and then going from that, so the next is weak nuclear force. Weak nuclear force is responsible for many of the nuclear decays. For example, if you consider a beta decay, it's a process of conversion of a neutron into proton and an electron, along with another particle is also going, which is called the neutrinos. I'll talk about neutrinos more in my next few slides. So I just want to tell you that the weak force, this is one of the examples where the weak force plays a major role. So these are the different four forces in nature and the corresponding particles which is exchanging during these particle interactions. So and this table explains the properties of forces. So again, I want to give you a relative strength of these forces. So suppose the strong force is in some unit. If you consider the value of strong force is 1, and then the electromagnetic force is 1 by 1000. That means 10 raised to minus 3. So that means that electromagnetic force is around 1000 times weaker than the strong force. Now I think you will understand why the nucleons are why the protons are bind together inside the nucleus, and the weak force is 10 raised to minus 16 times weaker than the strong force, and the gravitational force is the weakest of all these. And again, this is not the part of the standard model, which is around 10 raised to minus 41. So, and the other table, I mentioned what are the name of the carriers and symbols and the range and mass, etc. You can have a look at that later. So Again, this is the same picture which I showed in the previous slide, the standard model, like what for the particles in the standard model. So there are 6 quarks and 6 leptons and 4
Excuse
gauge
me,
bosons. And
excuse me, Navaneeth. Many are
yeah,
saying that your slides are not available for them. Only your talk they're getting. So something you might have done something with the slide. Can you share it again? Your slide.
sure, I can do that.
Yeah, many are saying so. I'm getting here. Maybe because I have pinned you in the first time itself. So many are now
Okay,
in the chat that they're not getting your slide, just your video only.
okay. I may try to uh, share it
So maybe
again.
all those participants who came late may not have pinned, and your sharing is not available now.
Okay,
Share it
I'll
again.
make sure. I'll make sure.
Okay.
Just a second. What about now? Can everybody see now?
It's available for us. Let's wait for a
Yeah,
few messages also.
yeah. I'm seeing yes messages. So
Okay.
maybe
Okay.
yeah. Please let me know in case if you have any trouble viewing these slides. Okay.
I think
Sorry about that.
many are commenting. They're getting now. So I think you may
Okay.
proceed.
Yeah. Okay. Sorry about that. Yeah. Okay.
And
I'll
one more request to all the participants. Please pin the presentation of Navaneeth. Then only you will be able to see his presentation. Thank you.
Oh, okay. So you might have missed the previous slides. So that's okay. But so yeah. So whatever I'm talking about, the standard model was was these particles which is given in this table. So there are 6 quarks and 6 leptons, and along with that there are 4 fundamental bosons, and bosons are the particles which as I mentioned responsible for the forces. So everything in the universe, like all the particles you are seeing, are made up of these 6 plus 6, 12 fundamental particles, and these particles have their own antiparticle also, and everything in this universe is made up of these 12 particles and these bosons. So today in my talk, so my research area is mainly focused on neutrinos, which are the lightest leptons. You can see the bottom 3, like electron neutrino, muon neutrino, and tau neutrino. I'm basically, my research is studying about the neutrinos. So I'll talk a little bit more about neutrinos, how we do the neutrino research, and I'll talk a little bit more about the properties of neutrinos and things like that. So moving into the next slide. As I mentioned, you all heard about the beta decay. So some nucleus, you know that they are not stable. So what happens? Those nucleus, they decay some particles and try to attain stability. So, for example, if you consider a carbon 14, so carbon 14 is a highly unstable thing. So but the nitrogen, which is 14, which is a stable thing. So what carbon try to do is try to emit an electron and try to stabilizes it. So again, these are the energies in the masses in MeVs. Also, if you add the left hand side and right hand side, you will get almost same mass, but you don't get exactly the same. I'll tell the reason in my coming slide. So this is actually a beta decay. Beta decay is the process of conversion of a neutron into a proton by the emission of an electron. So this was the picture in around 1930s. So today we know that is not exactly the beta decay. So that's an incomplete picture of beta decay, and there is one more particle is there. So I'm going to talk about that later. So here the beta decay, just put like in your mind, you know that it's a process of conversion of a neutron into proton by the emission of an electron. So the one problem with the beta decay spectrum, which is measured in early 1930s, that if it is a two body decay, so you know that the neutron is at rest and it is decaying into proton and an electron. So if that is the case, the total momentum has to be conserved, right? The total momentum of the outgoing particle should be zero, because the initial momentum of the particle is zero. So that's basically the momentum conservation. So it's like that the energy also should be conserved, and you know the masses of all the particles, and you can calculate the energy using Einstein's equation. And then if that is the case, so you know that the mass of proton is like fixed, mass of neutron is fixed, mass of electron is also fixed. So in that case, you would assume the energy of the electron coming out from this beta decay should peak around a one value. But what we are seeing is a continuous spectrum. So that means that the like an electron can take any energy. So that was actually not that was against the understanding of this beta decay. So what is happening here? So this is called the continuous beta decay spectrum. How one can expect or explain continuous beta decay spectrum? So this then in Pauli actually proposed that there is, along with this proton and neutron, there is another particle which is neutral, and a half spin particle is also emit during the beta decay. Then you can explain this continuous spectrum. How? So then the only thing is that sum of electron energy plus neutron energy should be a constant, but electron can take any energy. The remaining energy will be carried out by a neutrino. So that in that way you can explain the continuous spectrum of beta decay. So the neutrinos are proposed to explain the continuous beta decay spectrum, which is observed like in the carbon molecule. So at that time the neutron was not observed, so they used to call it neutron, and later then the neutron discovered, they changed it into like the change of the name into neutrino. The neutrino means tiny little particles, neutral particles. So why we study neutrinos? The neutrinos are the most abundant particles in the universe after photons. The photons are the most abundant particle. After the photons, the neutrinos are the most abundant particle. So in order to understand like our universe, so the only we know only a very little about the universe that we live. So we know that like the only 4% of the 4% of the visible matter is like only we understand only the 4%, and rest is still we don't know. So then they have the dark, they have you might have heard about dark energies and dark matter, which are actually the constituent of universe, which we don't know what these dark matter and dark energies are made up of. So we don't know much about this universe. So in order to understand the universe we live, we must understand the properties of these neutrinos and other fundamental particles also. Other fundamental particles we have learned a lot, but neutrinos are, since it is very tiny and it is neutral, it is very hard to study them. And but in order to get the complete picture of the universe we live in, so we need to understand the properties of neutrinos very well. So I will directly going into an interesting phenomena of neutrinos. So I told you there are three types of neutrinos: electron neutrino, muon neutrinos, and tau neutrinos. And that we generally call it flavor state: electron flavor, muon flavor, and tau flavor. That is what we used to refer them. So the neutrino oscillation, I'm not going to the history of the neutrino oscillation because of the lack of the time, but it's a very interesting topic. You can always go and read things in the website. So it's a very interesting phenomena. So what neutrino oscillation is? Suppose that you have a muon neutrinos, and when the muon neutrino travels, it can change its flavor into electron or tau. So that means that a muon neutrinos, when it travel, it can convert into it can oscillate into a electron neutrinos or a tau neutrino, and the phenomena of conversion of this flavor from one flavor state to another is called neutrino oscillation. And the neutrino oscillation is a purely a quantum mechanical phenomena. So it can be explained using simple quantum mechanics. So just put in your mind that the neutrino oscillation is the phenomena of changing the flavor of one neutrino from one flavor to another. So the neutrino oscillation was proposed in 1980s in order to explain some of the known problems, which are called solar neutrino problems and atmospheric neutrino problems. As I said, due to the lack of time, I'm not going into that detail. You can always go and read about that. And the neutrino oscillations was discovered in two large experiments. It's called Super Kamiok and Snow experiment. And these two people, Takaki Kachida and Arthur McDonald, they got the Nobel Prize for the discovery of these neutrino oscillation. The neutrino, there are many, like, Nobel Prize has been awarded in the area of neutrinos, and this one was the latest one, which is for establishing the neutrino do oscillate when it travels from one place to another. So I just want to give you an idea what the neutrino oscillation is. So the neutrino oscillation, as I mentioned, it's a very quantum mechanical phenomena. So you know that the waves, okay, you know that waves, associated waves, you can associate a particle which is vibrating with some frequency. This is some classical concept, and you can think of yeah. So if neutrinos, like an electron neutrino, muon neutrino, tau neutrinos, are, if you think that as a wave, so for the sake of the simplicity, I just take two flavor, electron neutrino and muon neutrino. So if you consider this as wave, so when you produce one electron neutrinos or muon neutrino in interactions as this wave, but what happens is that as it propagates, these waves will combine together and to form an interference kind of pattern. You know that if you add two waves with different frequency, you get different types of waves. It's basically, you might have studied a lot about this Fourier transform and things like that. So this is exactly that same process. Consider one electron flavor as one wave and the other flavor as another wave, and when it produces as wave, but when it when it starts propagating, it's propagating as a superposition of these waves. Okay, so this is again a little bit mathematics. You don't have to worry much about this. So you know that if you might have heard about this coordinate transformations. So if you have an x plane and xy plane, and you have another plane which is actually rotated about some like an angle, and you label that as x dash and y dash, and then you can connect the old coordinate and new coordinate using a rotation matrix, right? Similarly, I'm just talking how we can mathematically formulate the neutrino oscillation. The neutrino oscillation can be also think as the same. So here the neutrino oscillation, suppose you have electron neutrino and muon neutrino, so those are called the flavor state, as I mentioned in the previous slide. Those states actually produce in an interaction, but after that it will travel as a superposition of some different state, and that state is called a mass eigenstate. If it is too complicated, you don't have to worry about that. So the thing is that the flavor state and this mass state are connected by some rotation matrix. Okay, so that rotation matrix will tell you the properties of this neutrino mixing, so these neutrino oscillations. So if it is complicated, as I mentioned, you don't have to worry. Maybe here you will understand. So once you formulate the mathematics like that, so you can calculate the probability of an electron neutrino. Suppose a neutrino produced as an electron neutrino going into muon neutrino. You can write it in terms of, this is just using the previous mathematics, you can derive this formula. You can see that it is proportional to sine square 2 theta. Theta is the mixing angle, this angle theta, and then then it depends on the length that the neutrino travels and the energy of these neutrinos. and this is the this is called the probability of electron neutrino appear as a muon neutrino, and 1 minus of that probability will give you the survival probability of this electron. Survival probability means that suppose that you start with an electron neutrino, you what is the probability that you still see an electron neutrino after a time t. So that is called the survival probability. Okay, so here in the bottom plot, if you look at that, suppose that if you so you start with some 8 electron neutrino at some time t is equal to 0, and the probability curve is actually the probability of that electron neutrino going to muon neutrino is given by this curve, that is the red curve, and you can see that the probability is maximum around 400. Okay, that is the length. So if you consider there are 8 electron neutrinos as it travels, and you can see that according to this probability equations, here the probability is 0.8. That means that 80% of that electron neutrino will be converted into muon neutrino. That means that 6 of this muon neutrino is converted in, sorry, electron neutrino is converted into muon neutrino. And then again, if you look at that red curve, you can see that around 800, it is again the probability is 0, and that means that this muon neutrino can again oscillate back into electron neutrino. That means that the probability is 0. That means that you should see all the electron neutrino that you start with. So you will see around 8 electron neutrino itself here. So that is basically the fundamental the principle or fundamental theory behind the neutrino oscillation. So now I will explain how we study this. So I work in a Fermilab. We have an accelerators here, so we can produce neutrinos, and we make huge detectors to detect these neutrinos. And I can just tell you from this picture that my experiment is called DUNE experiment. It's called Deep Underground Neutrino Experiment. What we do here in Fermilab, we create the neutrinos from accelerators, and we send to a detector which is situated very close to this neutrino source in Fermilab, and then through the earth, the weak interactions are really weak. It can so the neutrinos can easily pass through the earth. So we send those neutrinos around 1,300 kilometer away, and we put another detector here. So we count the number of muon neutrinos. We basically produce muon neutrinos. We count the number of muon neutrinos at Fermilab, and then we count the number of muon neutrinos at South Dakota, which is around 1,300 kilometer away from Fermilab. And comparing these two data, we study the neutrino oscillation, and we see that how many neutrinos are survived or how many neutrinos are oscillated when it travels through the air. So that's what basically we do. So I can just show you a simple picture. It's a video how we make the neutrino beam. So I hope you can see. So this is actually a cartoon. So in Fermilab accelerators, so in Fermilab we have accelerators. So that accelerators are basically, we accelerate protons in that accelerators. So that protons is around 120 GeV. The energy of the proton is 120 GeV, and that proton, then we put a graphite target, and this proton will hit in the graphite target, and after when the proton interact with this graphene target, it produces other secondary particles like ions, pions, which are actually formed by the fundamental particles which I mentioned, and then those particles are highly unstable, and and depending upon which neutrinos you want, like I told you, there are neutrinos and antineutrinos, and you can, the neutrinos are neutral, so you cannot control neutrinos. Once it produces, you cannot control it using magnetic field. So what you do before that particle, a neutrino is produced, so we actually filter them. So we put a magnetic field here to select only the parent particle of electron neutrino, muon neutrino, not the anti-muon neutrinos, and that will decase into neutrinos that will decay into neutrinos, and some muons also will be there. And then we put a graphite target, sorry, some concrete block here, so that all the muon neutrino will be absorbed. And then we will left with only neutrino beam. So this is how we produce the neutrinos. I hope you understand. And then how once so I mentioned that neutrinos are very weak, so it interact only uh, very weakly. So how we, in order to detect them, so we make billions of neutrinos at Fermilabs, and then when we pass to the detector, only few of them will be interacting, because this is very weakly interacting. So this is I don't know whether you will understand that. So this is how, this is a detector, how we detect the neutrinos. You can probably see this is called a, we have a detector, which is, the detector volume is actually liquid argon. When the neutrino comes and hit the liquid argon, which produces some particles like electron or proton, and we basically study those protons and electrons. I can show this animation, maybe probably see. So this is our detector. So we have applied an electric field to this detector. So when a neutrino comes, and inside the detector there are liquid argon is there, the neutrino, few of the neutrino will interact inside the liquid argon, which will produce a proton and muon. So that muon, as the muon travels to the liquid argon, it ionizes the argon, and which produces an electron, and we actually, that electron will be drift towards our detectors, and we study that. So it will leave a track inside the detector. So this is how we detect the neutrinos. So there are a few more things. I don't know, we have time, or if you don't have the time, I will stop here. Otherwise, it may take another 10 minutes. So what should I do? Do we have time, or should I just stop here?
I think you may proceed with 10 more minutes, and then we can have some interaction. We have time till 10:30.
Okay, fine. So okay, in that case, I will mention okay. So I showed you how the neutrino interactions are. So basically, so when a neutrino comes and interact with the, the detector volume, so if it is an electron neutrino, which will produce an electron, and if it's a muon neutrino, which will produce a muon, and if it is a tau neutrino, which will produce a tau, and we are measuring actually that in India, which is called the INO, and which is going to come in Theni, beneath this, Theni hills. So the construction is going on. Maybe you guys can, work on this experiment in future. So with that, I will stop my presentation, and you can have if you have any question, you can ask me. Thank you.
I think if somebody has a doubt, you may please connect. Navneet, I think some of the questions are in the chat itself. Can you have a look at the chat?
Oh, sure. Uh, so, okay, I can see Tanmay Parida. How do you calculate the number of muon neutrinos? Again, as I said, in the neutrinos, we produce a large number of neutrinos, and which comes in our near detector, and then the near detector, a few of them will interact. Okay, this is actually a statistical thing. So when it interacts in the near detector, you can basically count how many interactions are there, and by counting that interactions, you can calculate the number of muon neutrinos or whatever neutrinos which comes in the detector. So that's the answer for that. And then there is another question by Isharan. How can we use neutrinos for detecting to study and to study the gravitational waves? So I hope he's asking how we can use neutrinos for detecting the gravitational waves. So you know that the gravitational waves has been detected in LIGO detectors. So the neutrinos, so you know that the gravitational waves are produced when large object like in a black hole merging, or some other massive object which collapse. That's the time when these gravitational waves are originating, and that you can detect here. So the neutrino, you cannot directly use the neutrino to detect the gravitational wave, but neutrinos are an extreme is a we call it a multi-messenger astronomy. So you can use our neutrino detectors uh, to see whether we can detect the neutrinos from those events. So you can basically look at the time when we detect the gravitational waves, and we can if we see some neutrinos from the in our detector in that exact time, you can basically look whether these neutrinos are from that source. That's how we use these neutrinos to kind of as a multi-messenger source for this gravitational wave. Sir, what that color means in a standard model? Color is just I mean, it doesn't mean anything to to distinguish. You can say it's as a quantum number. Okay, so like that all leptons, you assign a quantum number of lepton number, right? For an electron has a lepton number of one. Like that, the gluon has a color, like quantum number, you can say. So it doesn't mean it has some color in our normal sense. It's just you can consider that as a quantum number. So then there is another question, Gayatri. What is the role of electric field in liquid argon detector as neutrino interact weakly? Okay, so when the neutrino comes and interact in the liquid argon, it produces muons. Okay, that muons, as it travels to the liquid argon, it ionizes that argon, and that during that ionization, an electron will be produced. So what we are detecting, we are trying to collect all that electron in our detector. So by collecting that electrons, we can measure how much energy these neutrinos has deposited, and that is what the role of the electric field in a liquid argon. So we are basically collecting the electrons which is produced via the ionization of argon when this charged particle produced during a neutrino interactions travel through this liquid argon. So now does neutrinos have medical applications? Neutrinos as of now they don't have direct medical applications. Neutrons have medical application. They are using neutrons for this neutron therapy. And neutrinos as of now we don't we didn't completely understand neutrinos. We are still studying the neutrinos, but a lot of equipments like detector components which you are using for the neutrino detector technology, that can be used in medical field for various purposes in future. So I hope I answered all the questions which is in the chat box. If anybody have any questions, you can ask also.
Please raise your queries if you have. We
Oh
are.
yeah, so there is one more. How could we explore the upcoming observatory in India? Oh, okay. So if you are like I don't know, Justin Reggie. I mean, like if you are talking in terms of like an opportunity to work there, if you are a student, every year the TAFR is conducting an exams. If you appear for that exam, you will be if you qualify the interview also. You can actually work as a graduate student in INO. Many of my friends are doing that. So as a student, you can always appear for this exam. I don't know if you are a student, but anyway, so you can always go through that exam and then uh, always work in this upcoming neutrino detector. That's a very good opportunities if you like the particle physics. Are neutrinos are their own antiparticles? So we don't
Now,
know
that
that
was
yet.
a question
Okay.
from YouTube link, so I posted it here. That was a question from I think Sherlock. So I had to post it here because that was in the YouTube link.
Okay. So this is, are neutrinos are their own antiparticle? That is the question. Anyway,
Yes, yes.
so okay, so the neutrinos are their own antiparticle. That's the question. So we don't know that yet. So that is a part of study that we are doing. So if the neutrinos are their own antiparticles, we call that as a Majorana particles. Otherwise, we call it as Dirac particles. We are still studying if neutrinos are their own antiparticles or not. And so many experiments are happening around the world. One is called neutrinoless double beta decay. That means that a double beta decay experiment, that in which two neutrons gives two proton and two electron without a neutrinos. If we can um, test that experiment, then that means that the two neutrinos are antiparticle of each other, and then they just annihilate so that we cannot see that. So if we find something there, we can say that the neutrinos are their own antiparticle. That's called the neutrinoless double beta decay, but we don't know the answer for that question yet. Okay, Justin said he's a UG student. Yeah, of course. Yeah, you can appear for that exam and uh, get admission in TAFR to work on the high NO.
Okay, so shall we stop? No.
Yeah, I mean, yeah, I have answered all the questions, so I think maybe I'll just stop sharing.
Okay.
Yeah.
Okay, maybe we will finish it here. So, on behalf of the Department of Physics, SVR and SS College, Vazhoor, I extend a very heartfelt thanks and gratitude to our resource person, Dr. Navaneeth Poonthottathil, for accepting our invitation and joining us as a resource person today. So, thank you very much, Navaneeth. Then I would also like to thank our principal, Dr. M.R. Renuka ma'am. She is a constant support and motivation throughout our activities and things. So I extend our heartfelt thanks to ma'am also. Now, this webinar was a huge success because of your participation from maybe all over India. We had received almost 300 registrations, and we had to split up into this Google Meet as well as into a YouTube live streaming. So and we had some hiccups in between as well, because some of them lost connection, some of them had a problem with the slides. So anyway, all was with us throughout the program, I guess. So, and it has benefited, I believe. So thank you all the participants. You made this a grand event for us. Then I would like to thank all my colleagues here, especially Mr. Babin from Assistant Professor of Mathematics Department. He was basically the technical architect throughout this program. So thank you, Babin, too. Then finally, a big thanks to one and all. Hope you all had a wonderful session. Thank you. A request to all, please fill the feedback forms as well. This is necessary to issue a e-certificate. So the link is provided in the chat box. Kindly give your feedback forms at the earliest. Thank you.